Ah, no, pues wrong ending.
Quizás debería cortar la cámara porque
no hace nada.
No se ve nada.
Se te la vida.
Sí, claro.
Te puedo mostrar ahí al principio. ¿Tenés el control? No, eso. Yo creo que... Welcome everyone to second seminar of the semester. Thanks everyone for coming. We're very happy to have Cristobal Guzman from Universidad Católica who will talk about his latest work. So thank you, Cristobal.
Yeah, thanks for the invitation. It's a pleasure to be here. So what I'm going to talk about today is joint work with Yelena Diakonicolas from UC Berkeley, and it has been recently presented at the Conference of Learning Theory. And you can find an archive copy of it as well. So yeah, let me first of all motivate the setting of this of our work. So there is an increasing amount of evidence towards extension in computer power, and of course that motivates looking for alternative ways to still increase up our computational abilities. And in this sense, it has been a lot of interest in researching the power of parallelization in different computational problems. So the idea here is that you can split up your workload on different machines and then try to merge this information somehow in an efficient way. Okay, and this has been very successful in some classical problems. But what we want to investigate here is what's the role of this paradigm in the in the optimization setting. Okay, and let me say first, it's not that parallelization is not helpful in optimization. Of course it is. I mean, any kind of evaluation of a function or any kind of computation you're doing on an optimization problem can be parallelized, because in many cases this reduces to some kind of linear algebra problem, and of course for those kind of problems we have very efficient parallelization techniques. So in particular, what I'm thinking in continuous optimization, these are kind of objects you might be interested in computing. Of course, evaluating the function, computing gradients, any kind of Taylor expansion, it's something that you can parallelize effectively. Particularly when your problem comes from some kind of statistical setting, you have your function is some kind of approximate expectation based on a finite sum, then of course splitting the workload on many machines is going to be helpful. What we're investigating here is whether the optimization process itself can be parallelized. And by this I mean that instead of the traditional setting where you evaluate the behavior of a function around a point, you do this in multiple points at the same time. Okay? And the reason why this could be promising is because, in fact, very similar optimization settings have been successfully studied via parallelization. In particular, for submodular optimization, there has been a number of works showing that you can obtain parallel speedups. And in fact, the way they do this is looking by some kind of convex, continuous relaxations of the combinatorial problem. Not necessarily convex, but using things like multilinear extensions, which are basically continuous objects. So that motivated to understand this question in the continuous and more precisely in the convex setup. So let me now make the model precise. So let me even go one step back and talk about what the traditional model of Oracle-based optimization, So suppose you have a convex function you want to minimize, and you're aiming for some kind of target accuracy of epsilon. This is like an additive error. So what you would typically do is design an algorithm which would evaluate the function around some point x1, use this information to find a second query point x2. Then you can try to recollect this information to adapt your decisions and hopefully converge eventually to some approximate solution. Okay. So what we're going to assume here is that any kind of reasonable algorithm we're considering, it's the way it chooses how it moves on this feasible set, it's only based on some kind of local information about the function around this point. Okay? That's the idea of gradient-based methods or any kind of methods which are based on some kind of Taylor expansion on the function. Okay, so given that kind of oracle model, you can define given an algorithm, you can define its running time as the minimum number of queries you need to make before you reach this valley of epsilon solutions. Okay, and you can define complexity as kind of the minimax performance of any possible algorithm. So you're trying to search for the best algorithm in terms of the worst possible function for that algorithm. Okay, in terms of the number of queries you will be spending before you reach this valley. So this is exactly the kind of worst case complexity you would see in any kind of computational model. It's just we're restricting it to oracle-based methods which use local information of the function. You can relax this notion and consider what happens with the performance of randomized algorithms, and you can equivalently see randomized algorithms as probability distributions on deterministic algorithms. And then you replace this number of queries by the expected number of queries you would need to make before reaching these approximate solutions. Okay, but this is a complicated object to study, so people tend to understand randomized complexity by even further relaxing and looking at what people call distributional complexity. Distributional complexity is what comes from doing some kind of minimax change here. You switch the infimum algorithms and the supremum functions by looking at kind of the worst possible distribution of functions, and now you minimize over algorithms. So this has like a different kind of interpretation. It's like nature somehow chooses the family of functions that you'll be trying to solve, and then your algorithm can adapt to that distribution. But still, the performance is based on the expected running time.
So what is the delta?
Oh, sorry, these are like probability distributions on classes of functions in this case. And here are probability distributions on classes of algorithms. Yes. Okay, and finally, you can even relax this notion further and say, I'm not happy only with having like good average performance, but understand what happens with high probability. So you can fix some kind of confidence value gamma here and try to understand what's the minimum number of queries, so the probability of stopping before time tau is at least gamma. Okay, and actually this is the kind of notion we use in our work. Let me just mention that as soon as you can prove a lower bound for this problem, for this kind of computational model, you get lower bounds for all these others. So it's not too important that you know all the terms that are here. It's only important to understand intuitively what this definition says. It says that basically I want to get guarantees on certain number of iterations with certain probability. Okay, and what we'll show effectively is that for any kind of reasonable choice of this confidence parameter, this is going to be as high as what happens in worst case.
Is there a relationship between the complexity R versus complexity D?
Yes, yes. Definitely this one is smaller than this one because of the kind of minimax theorem, but the weak form. So its weak duality tells me that if I switch an infimum and supremum in this, I always decrease this value. And by the way, we don't know whether strong duality holds here. So, because it's an infinite set, so you cannot use this like standard LP. No, there is convexity. Like you can see everything. You could linearize it here because you're looking at this expectation. You could also relax this and look at expectation over distributions of functions and in algorithms. So everything linearizes when you relax in that form. the question is whether these spaces you have here,
Right, but this we don't know A, at least what kind of
yeah, it's not like compact or anything. I mean, it's even unclear how to define a topology on that. So definitely it's true that this is smaller than this, but we don't know whether equality holds. Okay. Okay. The other thing we care a lot about this on this work is understanding how geometry affects the convergence rates. Okay. And the reason for that is because there's many natural settings where non-Euclidean geometries come into place. Okay. And here, to make it very, very precise, we're going to stick to LP spaces. So basically, we're going to think that our optimization domain X is given by some ball on these norms. And just to show you how they look like, so when you have p equals 1 here, this is like a high-dimensional octahedron. P equals 2 is a standard spherical Euclidean ball. And p equals infinity is going to be like a high-dimensional cube. Okay? Why do we care about these kind of settings is actually many relevant problems can be modeled by using these kind of constraints. Okay? In particular, all kind of sparse recovery problems and the relaxations can be analyzed and solved using some kind of L1 setup. So if you've heard of compressed sensing, and there are also extensions that go beyond that, like matrix completion, which is like an spectral analog of L1. Even further, you can study more general atomic norms. All those kind of can be understood in an L1 kind of setting. Okay? And on the other hand, there's L-infinity setups appear, for instance, when you try to model things like max flow or multi-commodity flows. Okay? Actually, let me mention that, for instance, this paper by Sherman, it studies multi-commodity flow problems, and the way they do it is using some kind of non-local algorithm that circumvents lower bounds that we have proven in the past. So even though one can think that the local oracle model is natural, it's not necessarily the ultimate answer for designing optimal algorithms. Okay, so what's the state of the art in terms of null parallelization? This traditional model of query points in space. We have sharp upper and lower bounds on what the complexity or how the complexity behaves. In particular, you can see, when p is between 1 and 2, the behavior of the complexity doesn't depend significantly on p. Okay, and you have this like non-smooth case, which is pretty bad. It's 1 over epsilon squared. When your functions are smooth, you can use acceleration techniques and get much better dependence on epsilon.
What is the tilde?
Here's because, the upper bound is 1 over epsilon square root of epsilon, but the lower bounds that we have, you have to pay some logarithmic in dimension terms that we don't know how to avoid. So up to that log factors, yes. And logarithmic in dimension only, nothing else. Okay, but what's interesting is though, as p grows from 2 to infinity, the behavior of the complexity changes dramatically. So problems start getting harder. And they do in this very precise way to the limit where p is equal to infinity. The complexity is going to change. So you'll get dimension dependent factors. Okay?
So I think, so where is the normal thing in the original problem? Because your problem was minimizing f.
Yes. Mm-hmm.
Where was the normal thing about that?
Oh, yeah. I should say that. So the problems we're looking at, minimization problems, in this case for p-balls, what we're saying is that the domain is given in this form, right? And this function f must satisfy some regularity condition in terms of the p-norm. So, and then the norm you pick here is a dual norm of the p-norm, which is the conjugate thing, and then you'll have some smoothness constant or whatever, and then here you'll have x minus y.
But in the non-smooth case, this translates into what?
Non-smooth case means this kappa I'm choosing here is equal to 0. So non-smooth.
But then you don't have the gradient, right?
No. Let me clarify that. It's rather when this is 0 here, there is no term. There's just a constant, and what you're assuming is basically that these gradients are bounded in this norm. If you have smooth, which is p equals 1,
the subdifferential set is bounded.
is bounded. And the smooth case means that this thing is going to be Lipschitz continuous, the gradient of the function. Okay.
The non-smooth, you are considering non-smooth function?
Yeah. I'm going to show some examples, but these are piecewise linear functions, so they are.
There are two notions of smoothness. I think that the name smooth is very bad choice, by the way, because it creates this confusion. Smoothness is about differentiability. And here, smoothness is about the Lipschitz behavior of the gradient.
Yes.
So when you that kappa equals 0, you still have a gradient on the other side. So the question is,
you have a subgradient.
functions which are non-smooth.
Well, in the case kappa equals 0, these are the subgradients of f. So it's not that the function is differentiable. That's notation, let's say. Okay. Okay, so and what's interesting is that there is some kind of similar behavior in the smooth case. Okay, so you still have like p between 1 and 2. Things are basically the same. Complexity worsens, but in the limit, you even have like complexity rates which do not depend on dimension. Okay, so that's quite interesting. These results have been proved in several works, but let me say that the non-smooth case was completely characterized in this very classical work of Nemirovsky and Yudin. We were able to improve in somewhat recent work these non-smooth bounds to hold in this high probability setting. So all randomization doesn't help, and that's a nice conclusion. And the smooth case, there was basically one classical lower bound, which was due to Nemirovsky in the 80s, but that was only for p equals 2. It was based in some kind of quadratic minimization problem, was very specific. And what we did instead is some kind of reduction from non-smooth case to smooth case, and we kind of translated the lower bounds. So it's like a smoothing technique you apply for proving lower bounds.
So,
Yes.
still, something else to see. So, the non-smooth case, the kappa is 0, right?
Yes.
So it's just being bound.
Yes.
So you talk about the difference in the first row that it's being bounded according to different norms.
Yes.
It's bounded in.
No, but wait. So both things changes, right? Because how you're measuring smoothness, as say you increase p from 1 to infinity, these powers are going to change, and this shape of the domain is also going to change at the same time, right? Yes. If you fix the domain and you increase the power, the problem should only become, let me think.
If kappa is 0, the right hand side disappears.
It should become harder, right? Because you will be using, as you increase p, this norm is going to use a lower value of p. These things might become, this p conjugate norm is going to become smaller. And this one over here, it will become.
0, this is a constant, right?
Oh, you're thinking about the dependence on kappa. Sorry. You're thinking non-smooth case, the dependence on kappa. Yes.
So
Okay.
the non-smooth case, just the right hand side is just saying that this is bound.
Oh yeah. Let me actually write it down.
Even one is bounded in any one.
Yes. Now let me do that to clarify. When kappa is equal to 0, you can almost equivalently replace this condition by saying, and I'm gonna be careful here. Let's say mu, okay, for every g belonging to the subdifferential of f at any point x, and this is for every x in x. So that's the condition. Here I was being a bit sloppy because I just wanted to make something which was unified.
There's a difference in norm there, x, and in the gradient, the norm that you're bounding the function, makes all the difference in the complexity.
Yes.
In that second condition, you have mu which depends on the p you're considering.
Right. Because actually here, this dual norm I'm taking is the conjugate norm of the p I'm using. So both I'm increasing the shape of the domain. I'm using larger p balls, which allow me to have larger sets, and this is going to be changing. And this, as p grows, this p star becomes smaller, and that means that these terms are becoming smaller. So you can fit more functions here. So it's natural that the problems become harder as p increases. Okay. In which precise way, that's another question. But one should expect that problems become harder as p grows. Any other questions? Okay, so now let me go into what do we mean by parallelization here. So it's a very similar model. The only idea is that now our basically optimization procedure works in rounds. And at every round, I'm making multiple queries of the function. So instead of just having an x1 or xt for iteration t, now I have k different queries at iteration t. Yes. And then the first oracle provides some kind of local information about those points. It can be much more general than this, but this is to make it precise. Let's say I'm giving you the value of the function and the gradient. And you can think about as this some kind of distributed architecture where there's like full communication on, like, this denotes the different rounds, and these like different nodes in the vertical line are the different parallel queries you're making. So at every step, you can make your queries over here dependent on everything in the past, but these queries themselves are kind of conditionally independent from each other. Okay. So that's the model. We can provide the same kind of notion of running time, but now what I want to minimize is the number of rounds. Okay? So if any of my queries is good enough up to some point t, I'm going to say I succeeded. That's my running time. And then I can study the same kind of notions of complexity. Okay, so let me say this question was actually posed a while ago in a paper that unfortunately went unnoticed for a long time, this paper by Nemirovsky, and it made the first attempt to characterize this kind of oracle parallel model. And what he proves there is that basically for this like p equals infinity setting, a lower bound of this form. And let's translate this a little bit. Actually, let's even first look at what happened in the non-parallel case. This bound, d log 1 over epsilon, is sharp up to constant factors. Okay, so that's what you should expect for p equals infinity. What he proves instead is something weaker. It's something like d to the 1/3 log 1 over epsilon. Okay, and then there is this other factor which depends on the amount of parallelization we consider. Okay, but whenever k, the amount of parallelization, is polynomial in the dimension, this is only going to pay you a logarithmic factor in the dimension. So it's not helping you much. So just to wrap it up, there's still a d to the 2/3 gap with respect to the non-parallel setting. And he left us an open problem. What happened? Like, what's the real answer here? This question is still open, but there have been some interesting attempts recently. Okay, so is it clear what's happening here? Okay, so let me now go to what we did in our work. Basically, I'm going to summarize it that for sufficiently high dimensional problems, there is no way to exponentially reduce the complexity using parallel computation. As long as the amount of parallelization I'm using is polynomial in the dimension. Okay? Is that obvious? Okay. And I'm going to show you why. Okay? So more precisely, we get lower bounds, which are in some cases sharp, in some cases are not, and it's an interesting approach to resolve those cases. So here, for I'm keeping this lower bound by Nemirovsky, but we obtained something similar, but it's not our result. It's this classical work, and we get these lower bounds for all these different settings. Okay, and let me mention that those over here, these four, are tied up to constant or logarithmic in dimension factors. Okay, so there we get the right answer. These cases over here, unfortunately, not.
Just a reminder, the rotation omega, it means it's a lower.
It's a lower bound up to.
We don't know the.
We do know. I mean, there is a constant factor here, maybe,
Right.
And that I'm not specifying. And if there is a tilde, it means a lower bound with potentially some 1 over polylog d factor.
The theta
Yes.
was sharp, right? The
Yes.
theta rotation is lower than a.
Yes, right. So let me say that for these lower bounds to work, all these except for this one, you need that the dimension is sufficiently large. Okay, and sufficiently large in this case means polynomial in 1 over epsilon and logarithmic in the amount of parallelization you're considering. Let me say there have been also independent works that studied the case of p equals 2, and the techniques have some resemblance to us. And as I said before, these lower bounds in colors are not known to be tight. Okay. But these ones are. Up to constant factors, this is exactly what you would get with fully sequential methods. Okay. Okay, so let me explain in a nutshell what we're doing to prove these lower bounds. We consider a family of convex programs. I'm going to be random convex programs. Okay, not stochastic. I want to be very clear on that. These are deterministic convex programs for any random realization of the parameters. Okay. So this is really this kind of distributional setting where you kind of, nature prescribes a distribution on objectives, but then for any given random realization, there's a fixed function you're trying to minimize. If we want to prove lower bounds for this smooth setting, we need to use this smoothing operator, but that can be used in a pretty much black box way, so I'm going to ignore it for now. I'm going to say a little bit of this towards the end. It's important that the smoothing operator preserves convexity of the functions and respects the locality of the oracle so that all our arguments go through nicely.
What is a smoothing operator?
Well, one of them could be using infimal convolution with a smooth function. Others that have been considered are like using Gaussian smoothing, so it's like a stochastic. For any point, you integrate a Gaussian around that point with like small variance. So there's different ways to do this, but for instance, infimal convolution is, for our purposes, is the most effective one. Okay, so M over here is what we want to prove as lower bound. And basically the idea is that there's going to be these random vectors, Z1 through Zm. If you look over here, what you have is basically affine functions because these are constants. And what we're going to show is that at every round of computation, the algorithm will only be able to detect one of these functions. So on the first round, this algorithm is going to make many queries, but what's going to happen is that there's going to be some form of concentration that's going to make all these terms sufficiently small so that these offsets over here are going to make only the first term in this maximum going to be the maximum. Okay? So you're going to only be observing Z1 from your local oracle. Once you've done that, you're still going to have all these other random functions which are almost completely unknown to you, and you can sort of iterate this argument. As I said, delta is like an offset parameter that allows you to claim that these functions are like separated enough. And yes, also said that the idea is to make that at every round of queries, you only reveal one new vector. Okay, so more precisely, this is the statement of our theorem. There's many things over here, but let me unwrap it a little bit. For this version of the theorem, we need the feasible set to contain the ball of the respective norm we're interested in. That's not necessary, but makes this slightly more precise. We consider these random vectors which are independent and supported on the dual norm so that this function actually has the regularity that we required in the dual norm. And then we need these four properties. So the first one is some form of anti-concentration that requires that any convex combination of these random functions is sufficiently far away from zero. Yes? In our case, you're going to be picking zi's to be like plus minus ones or 0, things like that. Very simple. But you could also use things like Gaussians or... Yeah. Towards the end, I'm going to show what distributions we consider in our work. Okay, so basically we want that any kind of convex combination of these random vectors is sufficiently far away from 0. Then you also need some form of concentration, and the reason for that is because of this reason I explained here. You want to reveal only one new vector at every round. So you need that every time you pick a fixed x, the inner product with the CIs is small with high probability. Okay? we need some kind of bounds for this offset parameter delta. So it has to be sufficiently large so that actually these functions are separated, but it cannot be too large, otherwise the optimization problem becomes trivial. If delta is a constant, it doesn't even matter what happens with inner products. The function is going to be a constant, so it's not interesting. And finally, as I said, there is some smoothing operator that allows you to get a lower bound for the smooth case, but if you only care about the non-smooth one, you don't even need this part. Okay? So if you have these conditions, you can lower bound the high probability complexity by this M that is the number of random vectors we're picking. Okay? I'm going to go at least at a high level through the proof so you can make sense of these expressions. I mean, I said a little bit how they work, but I'd rather make it more precise. So let's look at this first property, the anti-concentration that I mentioned. So why do we care about this? Well, the role of this property is simply to guarantee that the convex program we're using has a low optimal value. Okay? And I mean, you can compute this given this function. Oh, here, by the way, I removed completely the smoothing part. I'm only going to be looking at the non-smooth case. So this is effectively, this is the function we're trying to minimize. This is the minimum value. You can upper bound this minus all the offset terms by just minus delta. Just don't care about that. And you can relax this discrete maximum using convex combinations. Okay? So you get this kind of expression. Now we're going to use minimax duality to switch this min and max over here. So we're going to get the maximum of convex combinations of this minimum over here. This thing we know is exactly minus the dual norm. Well, if X contains the unit ball, this is at least going to be the dual norm. Okay? And now that I have this max of minus, I can switch it to minus minimum. And this property over here guarantees that this minimum is sufficiently small with high probability. So as you can see, I mean, this kind of property, it's only needed for guaranteeing that this problem has sufficiently low optimal value. Okay, and this minus, the 4 over here is completely arbitrary. Something larger than 2 epsilon is going to do the job anyways. Okay, so the second property I mentioned is this concentration along marginal. So for any kind of fixed S, you have very low probability of going beyond delta. The reason for that is once you have this kind of concentration, what you will see is that somehow this, for any fixed S, if you plot the densities of these different random variables, those which are inside the max, they're all going to be something which are tightly concentrated. And these offsets over here are just going to be separating these densities sufficiently well. Okay? So you can even do the computation using the union bound. So what's the probability that any kind of random functions from these ZIs has some significant correlation with my queries, and that's very small. Yeah, just union bound is going to give me number of linear terms times number of queries, but you have this exponential term that basically eats everything up. That's for the first round of computation. So you can guarantee easily that in the first round you only learn Z1 because the oracle is local, can only depend on the maximum term. Once you've done that, there is some kind of slightly tricky conditioning because you know that these tails didn't lie on this region, right? Or anything to the right. So, but those events have such a small probability that you can sort of unconditioning it. So using some kind of careful application of Bayes' rule and so on, you can iterate this argument to say that at every round, with very high probability, you only learn one new of these CIs. Yes?
So how is this working in the parallel setting? So each node is sampling one of the Z's at the
No, see, that's the thing. So Z's are sampled in the beginning, and they're fixed forever.
With the M Z's?
Yes.
And then how does the parallel work?
Well, that's the thing. So we're assuming that we're in the local oracle of computation, so the algorithm doesn't know in principle what these ZIs are, right?
Yeah.
So you're going to make your first K queries, and those cannot depend on Z in any way, right? They're completely independent. If they're independent, they're suitable for this kind of concentration bound, right? So with very high probability, every evaluation of these Z's and X are going to lie in this in this kind of high probability regions, right? The point is that what's going to be then the maximum of this function f? Well, it's going to be the guy who were evaluated on C1, right? One of them. I don't know which one, but it's going to be one of them. And that's, like the information you're going to get from the oracle is exactly that. It's going to be Z1, the subgradient, and the value you would get on evaluating that x that that happened to be the largest over here. Okay? There is some implicit information though, because since you know that this guy is the maximum, all the other evaluations on this guy were sufficiently small so that you're, like say this red kind of density here, your random realization of this z didn't lie over here, right? But that event has extremely low probability. And then you have to argue what happens in the second stage. Well, the algorithm has some kind of implicit information, but you have to uncondition it in a certain way. You have to use Bayes' rule to argue that the probability of this algorithm kind of correlating well with this Z2 is still going to be small. Okay, and that actually is the most technically challenging part of the proof. Okay. Okay, so as a conclusion, even if we make polynomially many randomized queries, the function values will concentrate on whichever has been seen so far, right? So you're going to learn the first round, this Z1, Z2, Z3. You're only going to take m rounds before figuring out all these random vectors. Okay, so the point of these two previous parts is to argue that with high probability you have low optimal value and you have high value for every evaluation of the function that your algorithm made. And if you put these things together, you can lower bound this by epsilon. And here it's important that the offset parameter is not too large because you want to upper bound this delta m by epsilon. Okay? And that's the sketch of the proof. Okay, so I promised I was going to say something about local smoothing. As we analyze this non-smooth case, you can turn it into a lower bound for also the smooth setting, just considering some kind of function phi that you can use to kind of smooth out your function. So whatever construction I used before, you can plug in this smoothing and then argue in a very similar way. Okay, and here is a precise definition of this infimel convolution smoothing. Okay, the classical example is just regularizing using the square norm, but different norms might require different kernels. So for instance, let me mention LP spaces when p is between 1 and 2 do not have such thing, or any kind of smoothing is going to blow up with the dimension. So like the smoothing parameter is just too bad for being useful for a lower bound. However, when p runs between 2 and infinity, it's smoothable with a very nice function phi, so we can get lower bounds for the smooth case there. And very similar results also hold for spectral norms of p, like sum of p powers of singular values of a matrix. So you can translate these LP lower bounds to things for matrix problems as well. Okay. Also, what are the distributions we end up using? Well, turns out that for say p equals 2, but also for p between 1 and 2, you can use basically plus minus 1 random coordinates, IID, and then you just need to rescale it so that these guys are in the dual norm. So that's just a scaling parameter, but effectively these are just Rademacher sequences. And for p between 2 and infinity, unfortunately, if you use this thing, you're basically stuck with a 1 over epsilon squared lower bound. So you need to do something different. Turns out that what's helpful here is to make these distributions to have disjoint supports. Disjoint supports. I mean, so we'll pick Z1 to be supported on the first L coordinates for some parameter L, and then the second one on the second. So you lose a little bit because you have to increase your probability space. Here, I mean, everybody lies on top of each other, so there's no problem. But here, you definitely start losing because you have to split up your different vectors. And this is basically why the Nemirovsky lower bound gives you this weaker kind of dependence on D. It's because you have to pay, you need this L to be sufficiently large so that you can guarantee concentration, and then you did need disjointness of this vector, so then you pay in terms of the kind of what dimension this lower bound holds. Okay, finally. So I mentioned before that our lower bounds did give some suboptimal results in some cases, or conjectured to be suboptimal, because actually we don't know what's the parallel complexity in these cases. But definitely this proof technique runs into trouble for this L-infinity setup. And this also came in the work of Nemirovsky. As I said, you need this disjointness of the supports of these random vectors, and that makes the lower bound to lose a little bit because of the disjointness. The other case which is problematic is L1. And then it's unfortunate, like, we could in principle use the same distribution of these CIs to be plus minus 1, right? Actually, let me say, for p equals 1, this thing over here is just 1, right? So effectively, and if you think you need vectors in the infinity norm, so it's perfectly fine to pick things which are plus minus 1 here, because those will be bounded in the infinity norm. That's okay. The problem is that those vectors do not concentrate. In particular, for instance, if you evaluate with some canonical vector over here, the CI, you only observe the marginal of this thing. It's a uniform plus minus 1 vector, so it's not concentrating in any way. In fact, we recently learned via an interaction with Daniel Kane that the family of convex programs we proposed can be solved in constant number of parallel rounds using polynomial many queries. So it seems that this meta theorem just breaks in the way that is that we propose. And we have other examples of different distributions that also fail. So there seem to be like strong limitations on this meta theorem. However, I still mentioned that we have some kind of lower bounds, and we do this by using techniques from convex geometry. This is a technique we use in past work with Nemirovsky. The way you could get, let me go back to this. I mentioned that these spaces are not smoothable. And I still show some lower bounds for these cases. So there's no way to use this technique. You have to do something else. What we do is some kind of embedding technique. So the idea is that, let's say we have the L1 ball here. There's a classical result of Boretsky that shows that you can decrease the dimension of your space only by a constant factor. So still something which is proportional to D. And that cross section, so that slice over here, looks almost like a ball. Of course, the radius shrinks because you're looking at this sort of diagonal. So it shrinks substantially, but there's like a surrounding ellipsoid with constant factor loss here. What you can do now is look at this subspace and so embed a cube over here and build the hard instances from L infinity. And then you need to take care about how to lift this function to the whole space. You still need to have a function which is defined everywhere. And we do this just by extending the function by linearity and then putting some kind of wall so that things are not, basically everything interesting is happening on this cube that lies over here. And doing this, we get these like conjectured to be suboptimal lower bounds for non-smooth and smooth. Let me mention though that in the non-parallel case, so in this paper over here, we do get the tight bounds. And the reason why we are not getting things which are sharp is actually because the infinity lower bound is not sharp for the parallel case, or we don't know whether it's sharp. But since you're losing some dependency on dimension, then you're losing some power on the lower bound because this embedding is going to give you something strictly weaker.
Doesn't the error between the ball and the
yes, this ellipsoid, or yes, yes.
Play a role in that?
You pay a constant factor. So we're ignoring always constant factors, and that's why. Okay. So how am I on time, Diego? Oh, okay, perfect. I'm about to finish. So there's some other works. Turns out that this kind of question has created quite a bit of interest in the community. So as I mentioned before, there were independent works, in particular this one by Woodworth, Wang, Smith, McMahon, and Cerebro, where they study the lower bounds for the case of p equals 2. But perhaps the most interesting thing that they do is that they consider stochastic oracles. So they're looking at stochastic optimization in this parallel model. And they even look further and not only study this like full communication architecture, but other kinds of communication architecture. In particular, for instance, they have gaps in the complexity when you're looking at stochastic smooth optimization with intermittent communication. So that means that basically you have your K stations running things completely independently, and then just every once in a while they communicate. In that case, we don't have sharp upper and lower bounds for what's the optimal complexity, and that's potentially the most interesting practical setting when you're doing, distributed optimization. There's this other work by Acharya, Desai, Foster, and Sridharan, where they study distributed stochastic optimization, basically where you have M machines and you're splitting your IID samples on these M machines. Okay? And you want to still do this distributed optimization, but minimizing the amount of communication. Okay? There, what they show is basically that you can get rid of the dimension dependence. If you think that all these algorithms would have to exchange vectors, which are high dimensional, so that's a problem. But they combine things like using subgradient descent with some kind of a sparsification technique for candidate solutions, so that they can pass on these vectors without incurring dimension-dependent amount of communication. What's the problem there, though, is that since they're using some kind of subgradient or mirror descent, they have to, every station would have to run their iterative method with their own samples. Then they would exchange it. I mean, they would take the solution and move it to the next machine. So there's a high round complexity that you would pay by doing this. There's actually no parallelization in this algorithm. Everybody's doing everything sequentially, so it takes a long time. Yeah, it's a bit disappointing, but I mean, it's interesting that you can avoid this dimension dependence. So it would be cool if one could actually do something in parallel. Say every station would run subgradient descent independently, and then you would try to kind of combine these solutions that everyone got to get something even better, right? Some kind of boosting thing, which is completely unclear. So now, if you go even to the p equals 2 case, there has been even further work, and the complexity here gets quite interesting. So let me mention that all the works, including ours, up to last year, they require a very high dimensionality for the lower bound argument to hold. If you do the computations in our lower bound, we need dimension to be at least 1 over epsilon to the 6 for getting this kind of concentration. Okay. There has been some very recent work by Bubeck, Yang, Lee, and Sitford, which were able to push this high dimensionality region to 1 over epsilon to the 4. And what they do is using our technique, or Mirovsky's technique, and they combine it with some kind of wall function that sort of hides this vector even further. It's a nice technique. We consider wall functions when we're doing this, but the cool thing is that the wall functions that they use are random themselves. They depend on the random vectors. So that's, I guess that allows you to kind of push this high dimensionality regime even further. Okay. The other thing that they do in this work is that they're able to improve the parallel complexity when you're strictly below this 1 over epsilon to the 4. So what they do is they use this as stochastic smoothing, the one I mentioned using Gaussians. So if you have your function f, and it's say non-smooth, you can immediately smooth it by just sampling Gaussian perturbations of this x, doing all of them in parallel. That's going to give you gradients and Hessians, and so you can use higher order smooth methods with acceleration, and that gives them this d to the 1/3 over epsilon to the 2/3 complexity. Okay, it looks quite strange, but look, this d to the 1/3 also appeared in the previous lower bound by Nemirovsky. So there's something funny going on there. Perhaps that's, it's possible that the true parallel complexity is indeed of this form, but between log 1 over epsilon and epsilon to the 2/3, there's a lot in between. So definitely this is not giving you the full answer. So here for comparison, I just plotted the sequential complexity in red. We know that for low dimensions, this complexity is d log 1 over epsilon. It increases linearly depending on d up to 1 over epsilon squared, where the complexity stocks, right? We get things which are dimension independent. In the parallel setting, now we know that this epsilon to the 1/4, also the complexity stocks here. What happens in between is this thing that is unclear. So this kind of upper bound in this paper gives you strict improvements in this kind of region. And up to, I think, is like 1/epsilon. And we know that in low dimensions, I mean, I would bet that the answer is closer to this. So there's definitely a lot of gaps here that need to be figured out. Okay, so to conclude, let me restate what I said before. It is not possible to exponentially reduce the oracle complexity for parallel convex optimization, or using parallelization to improve on the non-parallel case, when the amount of parallelization we're considering is polynomial in the dimension. Okay? Yes?
I got lost there. So this means that the exponent in the cycle is not reduced by parallelization.
Exactly. I mean, let me say like this. If the complexity was polynomial in 1/epsilon, we proved that for high dimensional problems, still polynomial in 1/epsilon. The power, we don't know, because in some cases we have these weaker powers, right? Yes. We hope that, you can prove eventually that these things are of exactly the order, perhaps except for p equals infinity. I have some doubts there. But most of the cases actually is not even just that you cannot exponentially reduce, but you cannot even reduce up to a constant factor. As I said, most or some of these lower bounds are sharp and match what happens when you have no parallelization at all. And even you can go further and use these techniques to understand, problems in stochastic optimization, statistical learning, even go beyond things which are based on local oracles, like proximal methods. So definitely there is some room for using these techniques in other settings. And these give, very deep insights on how do optimal algorithms look. There's many open problems, but particularly for me, the most interesting one is try to resolve what happens for L1 or L infinity. I think that any kind of improvement there might require some widely different techniques and possibly some very nice mathematical insights. Also, as I said, there's even for p equals 2, it's not completely understood how these different regions of the complexity change as you go in higher dimensions. And perhaps the most practically interesting consideration would be to, incorporate communication constraints more effectively in the model. There's other related questions, and there has been quite a bit of interest, as I said, in all sort of parallelization and different limitations of optimization. In particularly one which is widely open at this point is understanding how memory affects the convergence rates of algorithms. So if you think that, we always assume that you can compute gradients and you keep them and you use Hessians, whatever. But what if your algorithm is limited and you only have, say, sublinear amount of memory or only linear amount of memory? Is that the case that prevents you doing things like, ellipsoid method, because those require quadratic amount of memory? So this question is towards what kind of algorithms that we're currently considering are, out of question when you limit the memory of the algorithm. Also, it's interesting to understand what happens when you limit the information that the oracle provides. We always assume that you compute gradients and Hessians, but maybe that's very expensive, and you want to give rather like a summary of those. So if now your oracle is based on first order information, but say has a sublinear amount of memory, entropy, say, how does that affect the convergence rate? There's many natural algorithms that actually use this idea, like Frank Wolf, right? Frank Wolf uses the gradient, but only gives you a summary of the gradient. It gives you the most aggressive direction for that linear function. And that's a compression of the gradient effectively, and that affects the convergence rate. So that, I think, there's certainly room for understanding, other techniques like gradient stratification and so on, should tell you something about what you can achieve once you limit your oracle in those forms. So yeah, that's it. Thank you very much.
processors,
Mhm.
it doesn't help. But that's what that's your statement.
I mean, what we proved is that it's not going to give you an exponential improvement, and that's already quite insightful, I think.
So if we use, what do we need to actually get the reduction? Should we use like an exponential? That is the exponential
Well,
that
if you aggressively go and, I mean, I know that some amount of parallelization trivializes the problem. Okay, so if you choose your k to be something like, then I can solve optimization problems in one round. Right? Because what you would do is like you have your set, you would choose a sufficiently fine net so that everybody's close up to this epsilon. And that's it. Because all your parallel queries are going to be if your function is Lipschitz, it doesn't change too much, right? So the optimum on this discrete set is going to be an approximate solution of the true problem. I mean, but between this and poly D, there is a huge, right? So for instance, what I don't know is whether maybe constant to the D gives you some answer. I'm personally not super interested in that question, but it's a valid question. Yes. Right. No, but and some of the things we do, I think you should be able to get. Maybe k poly d and 1 over epsilon. In some cases, you can definitely, not just poly d, but even incorporate the accuracy somehow. So that gives you extra power, right? No, this is stupid. I mean, d is larger than a polynomial in 1 over epsilon, so this is absorbed. Doesn't even matter for what we do. But for those intermediate regions, maybe it's interesting. Yes.
Table of complexities?
Yeah. Here, yes.
So you say in these 4 cases, the 1 over epsilon square, 1 over epsilon p,
yeah.
those are sharp bounds.
Right.
So there's a match between upper and lower bound.
Correct.
And the exponent are exactly the same for no parallelization.
Yes.
So in that case, we gain nothing.
No gain. Yes.
Okay. So it remains to know whether p equal 1.
Yes.
So is there a gain in the lower bound? The previous lower bound or what?
Oh, here?
Yeah.
I mean, this one is 1 to the epsilon squared.
Okay.
1 over epsilon squared. So it's huge.
Yes,
This one is less dramatic because this is 2/5 and the other one is, square root. So I don't remember. It's like 1/10, I think, additive error in the exponent.
But in that case, you don't know if those are
No.
matching upper bound.
No, we don't know. We don't know. What's it? Well, we know something which is quite funny. I should have included it in the slides. We know the following. So this is the L1 ball. So this problem, we get that lower bound. Now, if you look at the same function class, but you restrict your domain to have this form, so much smaller, this is like 1 over root d, we get a 1 over epsilon squared lower bound. So it seems to, I mean, but here's a funny thing, like it's not given, it's not a valid statement to say that if the complexity of a subset of a problem is something, the complexity of the larger set is at least the same. So we cannot conclude from this lower bound that we have a lower bound for the L1 ball. Yes, and the point is that our technique kind of exposes these random vectors when you query at these points. So that's why it breaks. But so I suspect that the answer for L1 should be this. It just needs some other techniques.
What about if I fix the class of functions that there are only some parameters which are random?
Mm-hmm.
And on top of that, you have an idea of the distribution. So you're not looking for worst case of the distributions, but you limit
Okay.
This would be more natural, right? You have an precise class, for instance, in machine learning.
Sure.
Precise class of functions,
Yes.
not these ones.
Yeah.
You have a precise form, and you already have some randomness on the data,
Yeah.
but you have an idea of the distribution.
What I expect there, I mean, certainly for the learning or stochastic optimization setting, let's say learning. Let's say learning, definitely. You should do much more aggressive things. The stochastic setting, I mean, what they do in this paper that I mentioned, unfortunately, somehow they use our technique and they sum a random Gaussian to that. So the stochastic part, unfortunately, it doesn't play a big role in the lower bound. It's rather they use these techniques and they combine it with some noise. And the noise shrinks at a rate 1/√n, and that's it. So what I expect, and I think it shouldn't be maybe very hard to prove, is that for statistical learning settings, you should be able to get much better round complexity, and that has to do with this paper that I mentioned. They reduce the communication quite a bit, but I think we should even be able to reduce the round complexity significantly, because there's so much structure in an IID stochastic problem, even in the learning setting, that is just basically you have your loss function is super limited. It's just like a mismatch between the inputs outputs, so it should be very, very well structured. So yes, the answer is I definitely expect that in the statistical learning setting you should be able to get much better than this.